is every system that we are going to deal with going to be a thin lens? I mean, the answer to that is obvious. That's not the case. And even in the exercises you've done so far in Oslo, the moment you put a slight thickness to the lens, you saw some numbers changed. And any real system, any real lens, you're never going to have a lens with no thickness. There is going to be a thickness. It may be very, very small compared to the other distances in your system, but it's never really zero, right? So, even if I am trying to analyze a single lens, I can't always neglect the thickness. That's one thing. Secondly, many optical systems comprise of several lenses, several imaging elements or several optical elements. So, is there some way I can arrive at an equation that helps me analyze these systems in a relatively simple way? Now, why did we start with the thin lens? Why did we make that assumption that we can ignore the thickness? Because it reduced the equation we had got, the imaging equation we had got, to a very simple equation. And it was very easy to make lots of analysis based on that simple equation. And all our distances were measured from the vertex of the lens. Right? We said focal lengths are measured from here, object distance, image distance, and everything was measured from there, and it was very simple to analyze your system. So, let's say we want to have a similar equation, a thin lens equation for a thick lens. Okay? If I could somehow have one single equation that allowed me to analyze a thick lens, I could analyze it in the same way I analyze a thin lens. That means I'll say, consider the focal length from this point, consider the object distance from this point. If I calculate, I'll say the image distance is the distance measured from this point. So, I somehow want to take the matrix that I have arrived at, the cascaded matrix that I have arrived at for a system with several optical elements in it, and convert that somehow into a matrix that represents a thin lens. It's not a thin lens, but I want to use an analysis that I was able to use with a thin lens on this system. So, I've got a thick lens, and a thick lens does not just mean a lens whose thickness I cannot ignore. It can also mean I have a lens system like this, and I'll say I want to consider this as one lens. The way I've drawn it here, each of these lenses is also not a thin lens because I have put some thickness there. I could even say, let me take a system which has a number of thin lenses, and I'll say this is plus f1, this is plus f2, this is minus f3. While each of these individual lenses is a thin lens, together the system plus the distances, again I can consider as what I say is a thick lens. Okay, so you will say thick lens, or you could say compound lens. So, what I want to do, because I think it will make my job of analyzing the system easier, is to arrive at, so my goal to arrive at a matrix that gives a thin lens representation of any system. Excuse me. Now, how am I going to do this? If I had a system as I have drawn, so there is an M1, there is an M2, there is an M3, and it could be any system. So, maybe I am cascading more. I mean, in fact, here I have to take the distances into account. So, you will cascade more matrices. But finally, I end up with a matrix M. That matrix M represents this system. I am now saying, let M equal this. I've calculated, and I have this system matrix. What I know that the determinant of this matrix is n by n dash, where n is the refractive index here and n dash is the refractive index here. We just discussed that, right? So that's one constraint I know, and I can't violate that. What I'm saying is, how do I convert this to some new matrix m dash which has these coefficients? Now, I've slightly modified, this is nothing but the thin lens matrix. I've slightly modified it because, as I mentioned in the beginning of the class, we derived the thin lens formulation assuming you had the same refractive index before and after the lens, right? So, our definition of 1 by f was n2 minus n1 by n1, 1 over r1 minus 1 over r2. Right? But I'm saying now, let's not say that this is n1 anymore, but you have a different refractive index after the lens, and that we're putting as n dash. So 1 by f is this, and that I'm calling this p, and I'm taking into account this refractive index, that is the refractive index after the lens, as this n dash. That's the final refractive index. So that's why you have, instead of just minus 1 by f or just minus p, you have minus p by n dash. N is the refractive index of object space, n dash is the refractive index of image space. Now I want to modify m and get m dash, but I don't want to modify my optical system. I want to say, can I somehow convert this matrix to the form of a thin lens, but I don't want to change my optical system. Right? I'm not saying change the system, I just want to change the way I analyze the system. So if that's the case, how do I convert one matrix to the other? What element can I add? Clearly, to convert it, I must change something, but I cannot change it by adding another lens, because if I add a lens, I'm changing the matrix itself, I'm changing the system itself. I cannot add a curved mirror. A curved mirror will change the optical system itself. What could I possibly do? What operation that can I carry out that doesn't change the fundamental nature of the optical system? In all the optical operations that we have looked at, what is the operation you could possibly do that doesn't change the fundamental operation of the optical system? What were the different matrices we looked at yesterday corresponding to optical operations? You can add a distance, right? I can add a distance. That doesn't change the power of the system. So I'm going to take a guess and say, let me take whatever my optical system is. This is my optical system. It's a black box. I don't know what is in it. It has the matrix M. I'm saying the refractive index n before it and the refractive index n dash after it. And now I'm saying, let's consider that I am adding a distance d before it and a distance d dash after it, and I'll call this plane h and this plane h dash. So I'm now going to calculate the matrix that takes into account these additional distances. What will that matrix be? Well, I will have, so let's call that mh dash, right? The ray first sees this distance, so the first matrix will be 1 d 0 1, right? The next matrix will be, of course, the system matrix, and the next matrix will be 1 d dash 0 1. Okay. Now, if you multiply this, what you will get, and let me just write it next. Okay. So my mh dash, when I multiply it, is finally going to give me this. That is the product of those three matrices. our goal was to make this a thin lens matrix. So now I will equate these two matrices, the coefficients or the arguments of these two matrices, right? So that will give me 4 equations. So what are those 4 equations? I know that A plus C d dash should be equal to 1. This long expression here, AD plus B plus C dd dash plus dd dash is equal to 0. This is a conjugate matrix. The next one is C is equal to minus P by n dash, and finally CD plus D is equal to n by n dash. Now what are the unknowns of this in this case? I have 3 unknowns basically, right? I have the power of this system, and of course I've added some distances. I don't know what those distances are. So these are the unknowns. So I have 3 unknowns and I have 4 equations. So I can solve for these unknowns, and then I can put them back into the 4th equation and check I haven't violated anything. Okay. So the second equation is a rather long one, so we wouldn't start with that. We can solve for P d small d d dash using this equation, and this equation. So 1, 3 and 4. Okay. So you're going to solve for these using 1, 3 and 4. Okay, clear up to this point? So if you actually do that solution, you will end up with these terms. P is equal to minus n dash C, small d is n by n dash minus d by C, and d dash is equal to 1 minus a by C. And if you substitute these 3 solutions into equation 2, you will end up with, so if you substitute in 2, you get AD minus BC, nothing but the ratio of the refractive indices, right? It's AD minus BC is nothing but the determinant of the matrix, right? And if you substitute it, please do that later, you can verify that this is what you get. So you know that you've done everything correctly. So what have we achieved? We have found out the location of 2 planes. How do those 2 planes help us? They have tremendous benefit now in analyzing a compound system. Why? Because I can treat this compound system like a thin lens. What does that mean? It means I can say from these planes, I will define focal lengths, I will define object image distances. Right? So if I take, if we took the thin lens the way we had taken it earlier, so we had taken a thin lens and drawn it like this, we said if this is a focal point, any ray from that focal point travels to the lens and will emerge parallel. Now I am saying I have a compound system. It has a number of optical elements in it. But forget all that, somehow based on all these elements I have defined 2 planes, right? Let's say one plane is here and one plane is here, right? This is my plane H, this is my plane H dash. Now I will say if this is the focal length of this, how do I just trace a ray? Forget this system. I can remove, I can erase these. That erases very nicely. I can erase these and I can then say, I will imagine that a ray traveling like this, sorry, I wanted to change color. A ray traveling like this will emerge parallel. Now it does not mean that within the system that is what is happening, right? But I will draw a ray to this point and then I will draw a ray coming out as parallel. We'll see in more detail as we go along, but basically what I'm doing by doing this is saying I don't have to look at individual components anymore. I use these principal planes, and in fact I will now define a focal length from this point to this plane. Earlier we defined it to the vertex of the lens. Right? Now I will define it to this plane. Okay, so let's do that in a little more detail. Okay. So, if I look at, let's take a thin lens again. Okay, we had the optical axis, we had a thin lens. If we had rays coming from this point, they emerged parallel, we call this F. If we had rays coming in parallel, they focus to a point, we call this length L. We might have said F1, F2, but for a thin lens, F1 is always going to be equal to F2. Okay? And more specifically, this is always called the front focal length. This is the back focal length. And you may see this abbreviation. So, for a thin lens, right, back focal length is always equal to front focal length. However, now in our representation of a compound lens, right, let's say I'm drawing a single lens here as representative of my compound lens. Okay, it may be a combination of lenses and distances. It's maybe just a thick lens. That's my representation. We have now defined two planes. So let's say those planes are here. Call this H and this is H dash. I have a distance D. I have a distance D dash. I have an object distance, let's say that's my object, and my object distance is measured from the plane. I have an image distance, and that is also measured from the plane. Sometimes sometimes different variables are used. What is the focal length in this case? Right? What are the focal lengths in this case? Well, I am going to measure focal lengths not from the vertex of the lens, but focal lengths will be measured from H and H dash, and these are called the principal planes of my optical system. So, this is H dash. So, this plane effective focal length and image distance measured from here. And similarly, this plane, this is the effective focal length and object distance measured from here. In a compound lens, front focal length need not be equal to the back focal length. And in fact, you could ask me, I've put the distances D and D dash rather vaguely. This end is clear, this end and this end are clear. They are from the principal planes. Where up to what point do I measure them on this end? Again, if my lens over here were a thin lens, then I would just say you will measure them from the vertex of the lens, and since it's a thin lens, the vertex of the lens for the front and the back are the same. Otherwise, if it's actually your optical system, the lens is a thick lens, it itself will have, that lens itself has principal planes, right? So I might say the principal plane of this lens, if this lens is as shown and not representative of a system with many different optical elements in it, then I will say this is the H of the lens, this is the H dash of the lens, and I would measure distances from the principal planes of that lens. But we can keep it simple right now and just say D and D dash are measured from the vertices, assuming that it's a thin lens. Then I will ask you a question. Have you noticed in Oslo that there is a term called effective focal length? Right? So right on the spreadsheet, the design spreadsheet, the rightmost corner has EFL, right? So we have something called effective focal length. Or short form EFL. Now that you have a little more knowledge about all of this, do you have any idea what that effective focal length is? Did you play around with it to see that how you had focal length? You, in your last exercise, you had to design a lens to have a particular focal length. Was the focal length and the effective focal length always the same value? So my question is focal length and effective focal length always the same? If thickness of lens is 0, so the focal length and the effective focal length are equal if you make the thickness of the lens 0. So go back and try that today when you're in the lab. Okay. So effective focal length is actually a definition. So let's say I took a lens, okay, and it's not a thin lens, okay. So that means I have rays that come, if they were coming in parallel, I don't know what happens inside, but we say that we know that they will focus to the, let's say there's no aberration, so they've all focused to this point here, and this is nothing. Okay, now this is where we say focal length, right? So focal length actually now you must redefine, because how do I write the focal length of this lens? For a thin lens, I would have said it is the point, rays are coming in like this, this is the optical axis, they are bending like this, so this distance is focal length. This is for a thin lens, but now we are no longer dealing with a thin lens. So what's the focal point now? How will I say what is the focal point now? From the principal plane. So this lens, you will be able to calculate for this lens alone what is the principal plane. There will be two principal planes, right, H and H dash. So the focal length will be this. It's the distance called effective focal length. So it's the distance from the second principal plane to the focal point. That is the focal length. When you design your system, this was actually the distance you were designing. If you took thickness as 0, you would have been designing this distance. But in any lens which has a thickness, you are actually, when you give a number and say design, so focal length is this, the distance that you are telling Oslo to control is the distance from the principal plane to the focal point. Now, that's not always something easily measurable, because the principal plane, as you've seen in the diagram I've drawn, in this case happens to lie within the lens. So something that's easier to measure is the distance from the vertex. So this is the back focal length. And so you'll see that's why if the lens has thickness, these two numbers are going to be different, because one is being measured from a principal plane, one is being measured from the vertex of the lens. In a thin lens, the vertex and the planes all lie at the same, on the axis they all lie at the same point, and so all the distances are measured from the same point. But obviously if it's a thick lens, that won't be the case. It is, so the question is, how do we see the principal planes? How do we? So you will have to calculate it. You will have to calculate it for a particular system. So Oslo will tell you, so either if you are manually calculating, you can, that's what we're going to do now. I'm going to work out an example where we calculate the location of the principal planes. But again in Oslo, they are doing that calculation, and if you go to one of the menu commands, it will give you the location of the principal planes. Okay. So you can do a calculation and get the principal. We have done that we just did the calculation. We used the derivation that I did just a little while earlier. Finally, we arrived at expressions for P, D and D dash, right? Small d and d dash. D and d dash are nothing but the location of the principal planes. So you can calculate them for any system, right? And how they were functions of what? A, B, C, D. So if you're given a system matrix, A, B, C, D, you're saying for a matrix, and you don't care what is inside that, but you're told this is a system matrix. Using that, you're calculating where the principal planes for this system exist, right? So let's do that. I have an example that I want to work out here. Okay, so let's say you had, so consider you have two lenses, one which is 15 centimeter focal length, another one is concave, so it is minus 20 centimeter focal length, and it's separated vertex to vertex by 25 centimeters. Okay, and let's say it's surrounded by air, everything is surrounded by air. Okay, so first I want you to calculate the ABCD matrix of this system. Okay. So I have basically F1, I have a distance of 25 centimeters, and then I have a lens F2, right? So what is the system matrix for this? So of course it sees the second lens later, so it's going to be 1 over 21. It's seeing a distance of 25 and sees the first lens first. What is it? 15. Okay, that's the system matrix for this system. Right. I'll give you the answers. You can check them later. Okay. Now we go back to that derivation we had done and we use those expressions. So we had found out that D, that was a location of the first principal plane, right? D is equal to n by n dash minus capital D by C. That is what we got, right? In our case, by the way, n by n dash is 1 because we have air everywhere. So that ratio is 1. So this works out to 12.5. D dash was 1 minus A by C, and this works out to minus 16.7. So now again, we have to be careful with our sign convention. Okay, there are, as usual in optics, many different sign conventions. So you have to be very clear about which one you're using, or if you're reading up something somewhere, you have to be clear about which sign convention they are using. If the distances, so we are going to use the sign convention we are going to use. If D and D dash are positive, right, we say they lie outside, and we'll see what I mean by this, outside the compound lens. Okay, so clearly if they're negative, they lie within the compound lens. In this case, one of these distances is positive, one of these distances is negative. Therefore, one of them lies outside the compound lens, one of them lies inside the compound lens. Okay. Now, what exactly is the picture we are going to draw over here? I'll start with my optical axis. I'm always so pleased when I get anything that looks somewhat like a straight line. Then I have a convex lens, right? This is f1 is 15 centimeters. Not exactly drawing these things to scale, okay? And then I have a concave lens here. f2 is equal to, what was it, 20 centimeters, minus 20 centimeters, right? What are the distances we have calculated? Well, we have 12.5. So, I am going to say it's 12.5. This is the location of H. This distance is 12.5. Again, if I consider f1 to be a thin lens, I will just say it's from the vertex. If, however, f1 itself was a thick lens, this distance of 12.5 would be from the first principal plane of the lens itself. That lens would have its principal planes. Okay. Right now, I am going to just draw it from the vertex. Okay. The other distance d dash is negative. That means by our sign convention, it lies within the compound lens, and so I am going to say it lies over here 16.7 units away, or everything is in centimeters. So, this is centimeters away, again either from the vertex if f2 is being considered to be a thin lens, or from the second principal plane of f2 if f2 is a thick lens. Okay, is that clear? Right. So, this is my H dash. This entire derivation said that we have got the matrix in this form, right? So, it is a conjugate matrix because that second coefficient, B coefficient is 0. So, in other words, we are saying H and H dash are conjugate planes. And another interesting thing is they are unit magnification planes. That means if I was tracing a ray, let us say I have some ray going through the system like this, bends over here, it is going through the system like this. The height at this plane, let us call it small h, and the height at this plane would be equal. So, there is no magnification when you compare the heights at these two planes, they are unit magnification planes. This is my back focal length, this is the effective focal length, right. So, they can be very different, and clearly you can see in a system with just two lenses, there will be a very big difference. When you were doing the exercise last week, if you had noticed, when you kept the thickness of the lens 0, back focal length and focal length and effective focal length were the same. If you increase the thickness, and you might not have increased it very much, I do not remember what the exercise is called for, but maybe you gave the lens a thickness of 2 millimeters or 3 millimeters, you would have seen a small difference between back focal length and effective focal length. But in a system with compound lenses, you could see that the back focal length and effective focal length could have a very large difference between them, right, because the principal plane lies well within the system. Okay. So, today's class we have just gone over some of the ideas of using matrix ray tracing methods, and from those ideas developed a matrix that allows you to analyze any optical system in terms of a thin lens. That means making the analysis simpler. Okay. In doing so, we defined some very important planes called the principal planes. Okay. And what we will do in the lab class is we will just cover some more points about these planes, which will allow you to do the lab class today, which is on designing and studying systems which are thick lens systems. Okay. We talked in a few classes back about numerical aperture, and I had shown you some figures to say how we define it, and we said n sin alpha. So, where would you think of, I mean, you might ask, my lens itself has to be a material of a different refractive index. So if I have a lens, clearly I'm choosing something other than air. But that's not the only place I change refractive index. If you go to numerical aperture, since you asked, I'm just bringing this up. This is an aside. If you go to numerical aperture of a system, remember numerical aperture related to how much you collected light, right? So if you look at the numerical aperture, it was this angle coming from an axial object point, n sine theta, where theta was this angle. You could increase the amount of light you collected by changing n. And so you actually can get microscope objectives. Okay, they are the optics which are right close to the sample. They are collecting light from the sample. And you can get what are called oil immersion microscope objectives. So they actually have oil in this region before the collecting lens, so that the refractive index is higher and the amount of light that's being collected is high. So that is one way of increasing how much light you collect. Okay, so while in our cases, in the kind of systems we are designing here, I normally will say there's air surrounding, right? And many cases the image, the object space and image space have the same refractive index. That need not always be true. Okay.